determine if the following series converges or diverges. Here we have got an, the terms an's are natural log n over n square. Now we can compare this series with known series, like let's say series bn, n from it starts from 2, so 2 to infinity, and bn's are, let's say this one, 1 over n square. Okay, now we can do the limit comparison test. Limit n goes to infinity of an over bn. Unfortunately, this test fails. Okay, so this is not the way to go. Then another option would be then natural log of n. If you graph this function, natural log of x, let's say, it will be about this, slowly increasing, and there is a function like this, like root x. So we can compare this with, let's say, this one. This is comparable with root n over n square, which is same as n raised to 1/2. 2 minus 1/2 is 3/2, so n raised to 3/2. And we know that this series converges because this n is bigger than 1. Okay, now we can do the same limit comparison test again. Limit of n goes to infinity of an over bn. If this limit is positive and finite, then both series behave the same. Since this converges, this one converges as well. Unfortunately, this test also fails, so we cannot apply this. And let's look at other tests, not the limit comparison. And natural log of n over n square, these are positive numbers because n starts at 2. And look at the bottom is bigger than the top. When n is very, very big, this bottom grows faster than top. That means they eventually go to 0. And natural log of, you can say x, this is continuous. So looks like we can use integral test, and that's the case. So for integral test, what we need, so we're gonna apply the integral test. For this, we have to have terms positive, and that's the case. Okay, positive for all n bigger than or equal to 2, because this series starts at 2, so this is positive. How about continuity? Continuous? Yes. This is continuous function, continuous, and this is not going to be 0, so their ratio is also continuous. And how about the nature eventually, because this one grows faster than this. You can see from the graph, that means this is decreasing, or we can say decreasing. In fact, we are supposed to let a function be writing in terms of x, same thing, natural log of x over x squared, and f is positive for all x bigger than or equal to 2, continuous and decreasing. Okay, because the bottom grows much faster than top. In fact, you can find the derivative of this function and show that the derivative is less than 0 for x bigger than or equal to 2. That means if the derivative is negative, that means the function is decreasing. You can do that, but I am just seeing from bottom being bigger than top, so that's the case. Okay, x squared. Now we need to find the following improper integral. So the series starts from 2, so we go from 2 to infinity of natural log of x over x squared dx. And if this integral converges, that means if we get a finite value for this limit, that means this series converges. Okay, and if this series diverges, this one diverges as well. So let's do it. And so this is same as we have to go. This is improper because of infinity. Let's say this is t. So 2 to t, and t goes to infinity of natural log of x over x squared dx. Now how do we integrate this? Natural log of x, maybe use substitution. If we take natural log of x as u, then du is 1 over x dx. But we have got 1 over x squared. Okay, 1 over x, 1 over x. So there will be one additional 1 over x. So we are in problem. We are in trouble. So not gonna work. It might work, but it will be complicated. Now we can convert this into a product and use the integration by parts. Let's see that 2 to t. Let's put natural log of x times 1 over x squared is same as x to the negative 2 dx. Integration by parts. Okay, so let me write here integration by parts. That's when we have u times dv, that is same as u times v minus integral v times du. Okay, so let u be natural log of x and dv be x to the negative 2 dx. Then du is 1 over x dx, and antiderivative is x raised to negative 2 plus 1, negative 1 over negative 1. Okay, then this becomes limit t going to infinity of u times v. So this is pretty much negative 1 over x natural log of x. So negative 1 over x natural log of x, and we need to evaluate from 2 to t. Okay, uv minus v times du, so is negative, so it becomes positive. 2 to t, 1 over x times 1 over x, 1 over x squared. 1 over x squared is same as x to the negative 2 dx. Okay, let's compute this. T going to infinity. Here we can put upper limit, then lower limit. So upper limit means replace x by t, so negative 1 over t natural log of t, that's upper limit, minus replace x by 2. So minus in here is negative, so it becomes plus 1 over 2 natural log of 2. By the way, natural log of 2 is a decimal number. This is just constant. Plus, let's integrate. This is x raised to negative 2 plus 1. Okay. Look at here. When we integrated x raised to negative 2, we got negative 1 over x. So we're going to get the same thing here as well. Okay, if we integrate x to the negative 2, that is negative 1 over x. And we are going from 2 to t, and eventually we have to take limit t infinity. Okay, so limit t to infinity of everything, negative 1 over t natural log of t plus this is 1/2 natural log of 2 plus, let's evaluate this at the upper limit, so negative 1 over t, that's the upper limit part, negative 1 over t minus lower limit, but there is a negative sign, so it becomes plus 1 over 2. Okay, now when t goes to infinity, when t is very very big, 1 over t, that will be 0. This is a constant, this is a constant. How about here, natural log of t over t when t goes to infinity. So let me do this separate. Okay, it's not that easy, so it wants itself. So let me do without negative sign. So we know that limit of natural log of x over x, this is kind of natural log of x over x. Okay, and when x goes to infinity, let me find the limit for this. When x goes to infinity, this is infinity over infinity, and indeterminate form. That means we can use the L'Hopital's rule. So using L'Hopital's rule, this is limit x going to infinity, derivative of natural log of x is 1 over x over derivative of x is 1, and when x goes to infinity, this one does not count anymore. 1 over very big is 0. that means this limit is in fact 0. Okay, so what are we left with? When t goes to infinity, this goes to 0, this goes to 0, we have 1/2 natural log of 2 plus 1/2, so which is a decimal number. Okay, that's a finite number, pretty much a decimal number. That means, look at here, this integral converges, and this integral was built from this series. That means this series converges. Okay, that implies the integral converges, or the integral is finite, converges. That means the given series, in our case, converges. Final